sometimes it's yeah, initially I want to talk about the potential energy you have. So what's this potential energy thing? I told you that the gravitational force, that's conservative in nature. Conservative in nature. Conservative means conservative. What does the conservative means? It the particular force, that whatever the work done by the force by the force depends on depends only on the initial and final points, right? Final points. That's what the conservative force means. So to do that, this is just a recap of what I have done. So don't worry about writing this. So suppose I have, I hope I have done this one also. Like, let us say this is the distance x you have lifted, and after that you have lifted the object to a distance of y. Suppose this entire thing is h is the height, then the potential energy up to here, that is mgx, and potential energy up to here will be mgy. From this point to this point it's mgy. The total will be mgh, and simply h is equal to x plus y. So I can write that this is the potential energy 1 and the potential energy 2, right? pe1 plus pe2 is pe total. So you can write like this, because for any kind of conservative force, this we have discussed in the earlier topics. What I have discussed that if you move horizontally, what is the problem is that you have the gravitational force which is working downwards, and the movement, the displacement is horizontal, mg is downwards, and hence the work done by the gravitational force that goes to zero. So these are, I just recapping the things what we have done earlier. And you got to know this equation, u final minus u initial is equal to negative of integral f bar dot dr bar, where the force f bar is a conservative force. So how do you check the given force is conservative? This also I have told you. This is fx I cap plus fy j cap. Suppose this thing is given to you. How do you check the given force is conservative? So you write dou fx by dou y, that is equal to dou fy by dou x, right? And dou fx by dou z is equal to dou fz by dou x, and dou fy by dou z is equal to dou fz by dou y. So even one of the condition, all the three conditions should be satisfied. Even one condition fails, you will say that f is non-conservative. Otherwise all the three conditions are satisfied, you will say that f is conservative. This is the just recap of the things what I have done in the earlier classes. And now based on that we will solve some few problems today, and uh, we'll see what are the things which will come next. So the given things. So can I clear this, everyone? Hopefully can I clear? I'll clear this off. So you have f is equal to the first problem, f is equal to 2x, and you have u at x is equal to 1 and is 10 joules, is 10 joules, and u at x equal to 2, you had to find how much. How do you find u at x equal to 2? So we use this basic equation, u final minus u initial is equal to negative of integral f bar dot dr bar, and here it's f is only 2x and your dr bar becomes dx here. So integral, you have negative 2x dx, and x is running from 1 to 2, so it changed to 1 to 2, and u final is u at x equal to 2 minus u at x equal to 1 is 10 joules, so you put 10 over here, so this becomes x square, integral 2x is x square, under the limits 1 to 2, and you have negative 1 over here. So when once you plug in the things, you have negative 1 times 4 minus 1, so that is minus 3 over here. U at x equal to 2 happens to be minus 10. When you send this side, you had 10 minus 3, which is 7 joules. This is what you get. You got 7 joules. That is 7 joules. You got it? Can I clear? Hopefully I can clear this. So the next question, question number 2, we'll see. So it's given f is equal to, you have 3i cap plus 4j cap plus 4j cap, and u 0 comma 1 is given as 10 joules now, and u at 2 comma 3 is what you had to find. How do we do that? Again, the same equation, u final minus u initial is equal to integral fx dx, negative of, and again minus integral fy dy. This is how we do. And u final is u2 comma 3, u initial is u0 comma 1, right? Negative of, the x is running from 0 to 2. Look at the x coordinates, 0 to 2. Fx is 3 dx minus integral, and the y coordinates running from 1 to 3, 1 to 3, and then this is y fy, that is 4 dy. So when you integrate and then see this, the u2 comma 3 u0 comma 1 is about 10 joules, so you have this. So integral 3 dx is minus 3 into x. The x should be substituted under the limit 0 to 2, and again 4 y, and y should be under the limits 1 to 3. So that is negative of 3 into 2 here, minus 4 into, again 3 minus 1, that is 2. So that is minus 6, minus 8, minus 14. So u2 comma 3 is negative 10. If you send that side, 10 minus 14, that is minus 4 joules. This is how you can see that minus 4 joules refers to there is a decrease in the kinetic energy. Sorry, there is a negative work done. It's what is, I would say that this is positive work done by the force, because the u final I got negative. So something like this. Okay. Another question, hopefully you are clear with this.
Yes, sir.
Yeah, good. Now the third, if they are giving 3 coordinates, how do you solve? The f bar is x square, okay, I cap plus y j cap plus z square k cap, like this is given. And u initial is 0 0 0 1 1. At 0 1 1 it's given as 10 joules now. And you had to find at 232. So these are the type of a same model question in 3 different kinds. So how do you solve this? Again, u final minus u initial, you will use negative of f bar dot dr bar. This one you have to remember this equation. Based on this, the questions will come. So integral x square dx, and x running from 0 to 2 now, and integral this is running from 1 to 3 y dy, and you have integral, the z is running from 1 to 2, and you have z square dz. That's how you solve the problem. And u initial you will substitute, that is 10 joules. So similar fashion you will end up with the u final. U at 232 will be about 1 joule. So this is the answer what you end up if when you do the integration sort of stuff, all the things after the calculation, you'll end up with this. Is this clear? First part.
Sir.
Yeah, good. Now there is one more concept, something called gravitational potential energy. Gravitational potential energy. See, we know that the potential energy term, the potential energy PE is equal to mgh. We know that this is very well, mgh. But this is applicable when this actually h, this equation h is very small height, okay, very small height compared to radius of the earth. In that condition you have this, okay, compared to radius of earth. So in that condition we use this equation, okay. In other sense, when we see the gravitation, we have another formula for the potential energy, that is negative of g m1 m2 divided by r. So that's how you get, this is the negative of potential energy, negative of gmm2 by r. So that's how, after writing, please let me know after writing this.
Yes, sir.
Yeah, clear?
Yes, sir.
Yeah, good. Now, so this is the, this is for r is for any distance. This is meant for any kind of distance, any distance. And then this is called gravitational potential energy. One of the m is the mass of earth, mass of earth. The other one is the mass what we considered, okay, we consider. One is the mass of the earth and the other one is the mass we considered. And now for all the practical calculations, we take the potential energy is equal to 0 on surface of the earth. We assume this, assume, okay, we assume that potential energy is equal to 0 on surface of earth, surface of the earth. On surface of the earth, this is how we start assuming. Now I had to deal with one question called the chain questions. Prior to that, I will tell you something called center of mass. So once finished, please let me know.
Yes, sir.
Clear? This one?
Yes, sir.
Yeah, good. Now, we see the next one is the center of mass, COM, center of mass. Center of mass. What is this center of mass? See, it is a geometrical point. Geometrical point where the entire mass of the object, entire mass of the object appears to be, this is most important, appears to be located at it, located at that particular point. That's what the center of mass is. Center of mass is actually geometrical point. So COM, center of mass, may carry the mass, or may not carry the mass. May not carry the mass. So the one of the important thing, for example, I will tell you, you will understand very soon. Please note it. Clear? Once noted, tell me.
Yes.
Okay, done. Now let's see different situations. If I assume a circular ring, so this is a circular ring, you can assume. Okay, or I think I have some shapes over here. I'll try. Yeah, that's a circular ring for you. Yeah, if you assume a circular ring, it's like this. You can think of the circular ring. So there's a top view and this is the bottom view, and this is really helpful. So you have you can consider a something like a straight line. Okay, here passing through here, a straight line which is passing through. Okay, it's actually the axis of the ring. Okay, that's the, I'm going into the rotational motion directly, don't worry. So here you see at this point, at center of the ring, it's a ring. At the center of the ring, do you have a mass? No, right? Center of the ring, you don't have mass. Assume the mass of the ring is m. The center of the ring, you don't have mass, but the center of mass of the ring is located at its center of the ring. COM, that is located at the center of the ring, but there is no mass there. But entire mass of the ring, for calculations, it will start appearing to be concentrated at that one particular point. Got it? So similarly, suppose I consider a kind of a chain situation. Okay, okay, the chains, it will be like this. Okay, this is how I'm just trying to draw the chain. Okay, this is how the chain looks like. Chains. Okay, this is how a chain look like. So I joined all the things together to get a chain. This is a chain. So how do you find the center of the mass of the chain? So simple. For any kind of chain, the situation is like this. Suppose this is the length of the chain. Exactly at the half of the midpoint of the chain. Midpoint of the chain will come at exactly half of the length. That's L by 2. That's L by 2. Half of the chain happens to be at L by 2, right? And now the center of mass is located exactly at the center of the chain. So if the mass of the length is m, the entire mass is appears to be concentrated at the center of the chain. Did you get this idea? Suppose I take a rod. Suppose I consider a rod. So how to consider a rod? Okay. So I have a rod. So if I have a rod, in fact, a cylindrical rod, in fact, you have a cylindrical rod like this. So on this rod, if I consider a scenario of this kind, this is a rod, and this is a rod. So you have some three-dimensional view. Maybe I can generate for you that. Fine. This is a rod. Are of you able to see this one? Yeah. Now, if I consider a uniform rod, I considered a uniform rod. A uniform rod is here, and then it has a mass of m. And now, assume that the length of the rod is L, and you can see that at the center of the rod, the entire mass m is appeared to be concentrated. The entire mass of the rod, at the center of the rod, it appears to be concentrated. So in fact, if you take a triangle, sorry, if you consider a triangle, kind of a sheet, and then what you do is you simply start drawing the medians. The entire mass of the triangle is concentrated at the geometric center of the triangle. Geometric center of the triangle is called the point of intersection of the medians, that is centroid. That is centroid. So if you consider triangle, the all the mass is it's just concentrated at the center of the triangle. That's the centroid of the triangle. It appears to be concentrated. Most important. This word is important. It appears to be concentrated. It's not concentrated that. It appears to be concentrated. Appears to be concentrated. So when you had to deal with the problems of chains or rods or any kind of lamina, then you had to look at its centroid. I hope you got the idea. The centroid of the triangle is what you need to look in. Clear? All of you? Hope clear. Can I clear this? Once you are clear, I will clear this, and then we'll move ahead with some few problems. Can I clear? Yeah, hopefully. Now, the problem is that they have given a situation of this kind. So this is the vertical. Now these things are fine. The vertical line. Now this is the horizontal. And now what they have given is a chain like this. They have given a chain like this. Okay. This is the case A. and the chain is situated at a height of h from the ground. This is the ground, and this is the height. Okay, and this is the height. You can go to the top. This is the height h. And now the case 2. Let me work out the case 2. And now this is the vertical, and then this is the horizontal. And now the case 2 is like you have the case 2 is like this. So the chain this time, think about this problem carefully. This time the chain is standing on the ground like this. Okay, initially the chain is standing on the ground like this. There's a case B. This is the ground. This is the level ground. Okay. And now in these two cases, there is a third case also. So the third case is pretty simple. We'll take this one. This looks much better. So we'll try to draw the lines. Right. Now the case 3 is like the chain is simply lying on the ground. Okay, these are the three cases. This is the ground. Okay, and now the question is that, so they have given the options. Option 1, UA is greater than UB is greater than UC. This is option 1. Option 2, UB greater than UA is greater than UC. Option 3 is UC is greater than UB is greater than UA. And now option D is all above. So these are the options which are given. You got to solve this question. So how do you deal this with the question? This question can be dealt by using the concept of center of mass. So you can see over here, what we do is, you see this chain. In this chain, I told you, you got to locate somewhere. The center is somewhere here. Okay. At this point, the mass M will rest. And then the potential energy in this case is UA. That's simply mgh. So no issues about this. So if I assume this capital M, then you get capital mgh. Clear? The mass of the chain is capital M. And now coming to the second case, where the mass of the chain will be, it's exactly at the center of this one, the center of mass. But this is in the midway, right? Suppose the chain length is also h. We assume the chain length to be h, then only this is possible to solve this. Chain length of the chain is also h. Length of chain is equal to h. In this condition only we can do. So this one, if you see, the center of mass is lying at the height of h by 2. So UB case, you will get mgh whole divided by 2. Hopefully you got this, why it is, because you got to look at the height where the center of mass will be there. COM. And now in this case is on the ground. UC is 0. So which one is the correct option? The option 1. Is this clear? Clear? Can I clear this, everyone? Written? Hope I can clear. Everyone writing this, or can I clear? I didn't get any response yet. Okay, hope I can clear this. The next one, there is another question. You have a scenario that the a chain is bent in the form of an arc, which would form a quarter circle. It forms a quarter circle. What is this quarter circle? I'll explain that. You don't have to worry about the derivation here, but these are probable for the exam. So it is bent like this. You can see the chain is like an arc. Okay. And now this is 90 degrees. Now, if the chain is bent like this, so if the mass of the chain, this is R and this is R, mass of chain is equal to M. The potential energy of chain is given by 2m by pi gr. So this is very important. So if it is bent in the form of a quarter arc, in the form of a arc which would form a quarter circle, it is called quarter circle, chain bent as a quarter circle. The potential energy in that case is given by 2m by pi gr. This can be a very important bit. What are the things they can give you here in order to calculate? You will understand solving the problem. So can I clear this one? Okay, please let me know once it is over. Can I clear, or you're noting? Don't worry about the derivation part. It takes a lot of time if I have to solve all the derivations for you. So please remember this like a formula, and then we'll go ahead with the problem. So how the problem will look like is like this. A chain of mass 10 pi kg. So they have given like this, to numbers cancel, is bent in the form of a quarter circle circular arc. It's bent in the form of a quarter circular arc, and now of arc of radius 5 meters. Okay, and now find its potential energy. That's all the question is. So it's a bent in this quarter circular arc. If that situation is coming, 2m by pi into gr. You can take g as 10 meter second power minus 2. This is the question. So here 2 into the mass of the chain is 10 pi kg whole divided by pi times g is 10, r is 5 meters. So you can see this gets cancelled over, and then so that's about 1000 joules. That's how you can find the energy. I think this chapter gets over in another, maybe by this coming weekend, we'll finish off this chapter, and then we will be doing the rotational dynamics. So once noted, please let me know if it is clear.
Yes, sir.
Yeah, good. So the next one is potential energy of the springs. What's the potential energy in the case of a spring? So how do we take the potential energy in the case of a spring is given by half kx square. So how do we get this condition? Is what this is one of the important even for your board examinations. So it doesn't take much of time for this derivation. It's, let us say the mass is m, and now it's the spring is extended. It's already have an extension of x1, and it's further extended to an extension of x2, let us say. So when this happens, the work done from x1 to x2 is what we have to calculate. The work done is given by negative of integral, you can say f dx. So okay, this f dx, you can say f is equal to minus kx, you will substitute. So you have integral minus kx dx, and the extension is from x1 to x2. When you substitute that k is a constant, the k is called the force constant. So you have negative of k by 2 into x2 square minus x1 square. And I said the spring forces are conservative. Spring force F is equal to negative of kx is conservative. So as this force is conservative, the negative of work done is the potential energy. So the potential energy of the spring case is half k into x2 square minus x1 square. That's the potential energy. Now choose x1 is equal to 0, then and x2 is equal to x. We can choose like this. After the choice, you have the u is this equation, half kx square, and that's the equation for the potential energy of the spring. Okay. And now another important point is that potential energy of the spring is always a positive quantity. Once finished, please let me know.
Yes, sir.
Finished. Good. Now, after this, so another important point, gravitational potential energy can be negative or positive. Next, this based on this, the question can come. I mean, it's exactly straight bit. Potential energy of a spring is always positive. Means the question can be like, so they can ask you like, what are the following? Which one is the correct? Which one is the wrong? Okay, right. Potential energy of the spring can be negative or positive. Potential energy of the spring is always negative. Potential energy of the spring is always positive. None of this. So like this, a question can come. So for that, you have to remember this point. Potential energy of the spring is always positive. Gravitational potential energy can be negative or positive. And now the third thing is that you have the another thing is electrostatic potential energy. Electrostatic potential energy can be negative or positive. Based on this, also the questions can arise. You should not struggle at that point. Can I clear this?
Yes, sir.
Okay, good. Now we have now calculate the work done. Calculate the work done by the spring force and change in potential energy of the spring. So these two you had to do. So here goes the problem. So this is spring, and with this a mass m is attached. They didn't tell anything about the mass, but they have told us the extensions what they have. This is about 1 meter, and after that this is about 2 meter. They have extended. Initially there is an extension of 1 meter, that is x1 is 1 meter. This they have not given, but I am giving you x2 is 2 meters. This is what they have given us. That's all they have given. And find the work done and the change in the potential energy of the spring. So I told you the spring force is a conservative force. So the work done is nothing but negative of change in the kinetic energy, potential energy. Sorry. So delta W conservative force is negative of the potential energy of the spring. So based on this idea, you know the potential energy of the spring is half K into x2 square minus x1 square. So I just told you this formula. So this the force constant, they have given it as about 50, as the K value they have given it as 50. So that's what they have given. The 15 as actually Newton meter power minus so what's the unit of the force constant? So that is kx, so it's Newton meter power minus 1. Yeah, this is what they have given us. So we got to calculate the this one. So half into 50, the unit is 100, sorry, the unit is 100 Newton meter inverse. This is what they have given. So 100 half into 100 into x2 square, that is x2 square is 2 square minus 1 square. So here it cancels out to be 50. So it is 50 into 3. The 150 joules is the change in the potential energy. And now the work done by the spring force, delta W work done by the spring force is negative of the potential energy. So that is negative 150 joules. So based on this, the options they can interchange and they can give you. So at the end of the day, you should not get confused with that. Clear?
Yes, sir.
Yeah, good. Now we have, so on top of it, you have a spring, which is like this. This is a question. The mass M is like this. It was hung like this in the case A, and this is mg, which is downwards, and spring force will act upwards. That is FSP, that is negative of kx. You all know this. And now, if the spring is a load to extend gradually to a length of x, so then you can say the spring force FSP is equal to minus kx. That is in balance with the force, gravitational force mg. So this is how you write. And now taking the modulus on either side, you have kx is equal to mg. Taking the modulus on either side, why modulus is because we want to see what is the magnitude of the extension. The magnitude of extension you can derive as mg by k. This is the situation where the spring is is being allowed to extend gradually. The spring is allowed to extend gradually. In that case, you will get it. And now how to calculate the potential energy? The potential energy is half kx square. And now the x is the extension mg by k. Substitute over here, half k into x square is m square g square divided by k square. So that is m square g square divided by 2k. This is how you get the potential energy. Can I clear?
Yes, sir.
So this is another important formula. This is the spring is allowed to extend gradually to the length of x. Earlier I told you if it is not allowed to extend gradually, then the kinetic energy will come into the picture. That's part of the work energy theorem. Now, after this, we have, suppose the spring situation once again. The spring is extended to a length of x, of course. And now it is at a height of h from the ground. Now spring is at a height of h from the ground. So it comprises of two factors of potential energy. The potential energy comprises of two factors. One is mgh, the other one is half kx square, both. But now we have derived the equation. What is half kx square? X is equal to mg by k. When you substitute, we got here, this is the total potential energy of the spring, mgh plus half k into m square g square whole divided by k square. So you have mgh plus mg by m square g square divided by 2k. This is what you get. And now mg, if you take common, you get h plus mg by 2k. So this is the total potential energy. Okay, total potential energy. This is the total potential energy. Once finished, please let me know.
Yes, sir.
Clear. Good. Now, after this, we have another concept called types of equilibrium. Almost this is like the last concept. Types of equilibrium. Once this is done, almost our chapter is over. I thought that I may be able to cover. Oh, it's getting over. The time is getting over. Maybe one more class we can finish this types of equilibrium. Just I will introduce the types of equilibrium for you today. So after this conservation of energy, okay, not much the conservation of energy. Okay, we'll see that. So once one more class, that this one will be over. Within one more class maybe. So maybe Monday we get another session. Maybe in that session we can finish this off, this equilibrium things. So the types of equilibrium. So here we go. Like you have one. So how do you do this? Okay, there are three types of equilibrium you have. One is called a stable equilibrium. Stable equilibrium. You have another thing called unstable equilibrium. Unstable equilibrium. And you have third thing, which is neutral equilibrium. Neutral equilibrium. So these are the three things what you had to know. So for the stable equilibrium, the U is minimum. For unstable equilibrium, it is U is maximum. And neutral equilibrium, U remains constant. U means potential energy. U means potential energy. U remains constant. So these are the three things what you have to remember for dealing with the stable, unstable, and neutral equilibria. Okay. Make a note.
Yes, sir.
Okay, good. Now we see the, how do you see this one? So how do we deal with this the equilibrium? When do we say that when do we say that equilibrium exists? When do we say that the equilibrium exists? So it's like when the equilibrium exists when the F net is 0. So it's like sum of the, in fact, vector sum of all the forces. Vector sum of all the forces is 0, then we will say that equilibrium exists. Say that equilibrium exists. Then we'd say that the equilibrium exists. And the vector sum of all the forces is 0. So these are the questions based on graphs actually. This particular stable equilibrium based questions are related to graphs pertaining to U versus X type graphs. So I'll give you a glimpse of that. With that, we'll close today the session. So what is a glimpse of that? So here you go. Suppose you draw the curve U versus X curve. When you draw, suppose you have something like this and then move like this and then go like this. And now what you are supposed to do, draw tangents, and where slope becomes zero, is zero. That means find the positions where we can draw tangents parallel to x-axis. This is what you have to do. Find the positions where you can draw the tangents to the x-axis. Suppose this is the point I take, I can draw a tangent parallel to x-axis here. If I take this point, I can draw a tangent parallel to x-axis. If I take this point, this is a constant anyway. So here, this slope in this case, the slope is nothing but dou u by dou x. That is zero. Dou u by dou x is zero, means f net is zero. Please understand. So here also dou u by dou x, that's the slope of tangent, that is equal to zero. That means f net is zero. So this line goes constant. So this also f net is zero. Now I told you what is a stable equilibrium. When you see the minimum, this is the minimum of the curve. So this is stable equilibrium. This is the maximum of the curve, but I still get the slope of the tangent is equal to zero. This is maximum. So this is unstable equilibrium. And the u remains constant here. So this is neutral equilibrium. Neutral equilibrium. So this is the concept today. Hope this is the time given allotted to us. So I think the next class, the next session will continue this further. I think almost once this is completed, I'll explain the differences between types of equilibrium and some few questions with that, and then conservation of motion. Yeah, almost the concept. These are little bit advanced problems. That problems you need not worry about. So this much, if it is done, that is sufficient, and then we can start rotational dynamics very soon by next week when we meet. So the Saturday we have, Monday we have another class, I hope. So Monday evening, and that we'll discuss these things further, and then try to finish off this chapter, and then I will move on to rotational dynamics. Okay, you can note it at this point.
Yes, sir.
Yeah. వాటర్ కావాలంటే వాటర్ బాటిల్ ఇందాక నువ్వేమన్నా తొందరగా చెప్పు. నాకు వాటర్ కావాలి ఫస్ట్ వాటర్ కావాలి తొందరగా. So can I close this? I hope I can close, and then we'll switch over to the, I had to switch over to the next class. Bottle. బాటిల్ బాటిల్లో కావాలి. ఓకే.